So since we just talked about derivatives in the last video, we're now going to talk about integrals, which are, as you can say, the opposite operation of the derivative, as you call them, the anti-derivatives. So now we will look into taking the integral of x. As you can see on the board, the integral of x is equal to 1/2 x squared plus c. This takes into account the use of the power rule. However, this power rule is not the same as the derivative power rule. It is the opposite. It can be generally written as 1/n x to the n plus 1. So instead of subtracting like we do with the derivative, you add to the exponent. And this plus c is very key. If you don't remember, your calculus teacher probably tried to ingrain it into your head. Plus c, always with integrals, unless it is a definite integral. This accounts for the added constant that we do not know, because we have no initial conditions. So we will now move on and look at the integral of 1/x dx. This might look like a simple problem. However, this is a special case. You can't just use the quotient rule. For 1/x, this is ln of x plus c. This is key in solving differential equations, which you will definitely have to learn about in linearity. Also, as we move on, we will look at the integral of e to the x. So you might look at this and be very confused and not sure what e to the x dx, how you take the integral of e to the x dx. However, this is actually a trick because it is very simple. This is just e to the x plus c. It's amazing. When you have the integral of e to the 5x dx, you still have to use the chain rule in order to take it. However, this is once again not the chain rule that is used in the derivative strictly. This right here, you get 1/5 e to the 5x. So instead of multiplying like for the derivatives, you divide by the constant, by the derivative of the exponent. That's what I should say. And our final integral we're going to look at is the integral of sine x dx. Sine and cosine have an interesting relationship, and they are out of phase with each other by 90 degrees. So this kind of oscillation shows up in their integrals and derivatives. So when you take the integral of sine x dx, you get negative cosine of x plus c. And when you take the integral of cosine of x, you get a positive sine of x. We're going to look into the integration by parts. So you set up the integration by parts by saying the integral of v du is equal to uv minus the integral of u dv. So this may make no sense to you if you didn't learn it, or you may remember this, or maybe you even never saw it this way and used the integration by parts without even writing this formula down. I know I did. So we're going to give you an example. We're going to take the integral of t e to the negative st dt. So as you can see, there's no way to really solve this out. You can't really use u sub. You can't really use any of the other chain rules or power rules or quotient rules to solve out this problem. So we're going to have to use this new method. So basically what we're going to do is we're going to set one of these variables, these can be split up into two functions, and we're going to look at them in t and e to the negative s of t. Basically what we want to do is we want to set one of them to where we have to take the derivative of it, and the other one to where we have to take the integral of it. So we're going to say u is equal to t. we're going to say dv is equal to e to the negative st. This means that we're going to have to take the integral of e to the negative st. And we just did this with e to the x and e to the 5x. We're also then going to have to take the derivative of t. When you take the derivative of t, you get 1, and when you take the integral of e to the negative s of t, you get 1 over s, negative s, times e to the negative st, as seen on the board. When you set this up, you now have to use the formula, and so you now plug everything in to set up the equation. However, you look at this and you're like, oh wait, this one we already have looked at this before. This is the original equation. What are we supposed to do? So as you can see, that top equation is the same as the bottom equation, except for we've solved for the integral of t to the e to the negative s of t. And as you can see, this is the original problem we were trying to solve. However, we now know more information, so we can see what's on the right side of the board and on the equation. Here we can simplify the right side even more by taking the integral of e to the negative s of t. This is 1 over s squared times negative 1 e to the negative s of t plus my negative t over s e to the negative s of t. Here you can take out e to the negative s of t. So you get negative 1 over s squared minus t over s times e to the negative s of t. This is all equal to the integral of t, e to the negative s of t. As we can see, this can be simplified to negative e to the negative s of t divided by s squared times s of t, or s times t plus 1. And before we go, this, without realizing it, you have taken the first steps to solving the Laplace transform. You have no idea what that is, and you probably don't care at this moment in time, but you will. Oh, you will.